So, this is the lecture 2 of module 2 in our course on intelligent control. This is the module 2 that covers the fuzzy logic concepts. Today we will be discussing fuzzy relation. Last class we discussed fuzzy sets, some introductory ideas, how fuzzy set was different from crisp set, and the concept of membership function, fuzzy operations. We gave some examples to illustrate fuzzy operation. Today we will be talking about fuzzy relation. So, topics that we will be covering today is extension principle of fuzzy sets, fuzzy relation, projection of fuzzy relation, cylindrical extension of fuzzy relation, fuzzy max min and max product composition operation. You see here, this is extension principle of fuzzy set. So, this is our fuzzy set A. So, as usual in the last class we said that fuzzy set is always an ordered pair where the member and associated membership function. So, there are n elements here x1, x2 up to xn, similarly y1, y2 up to yn. So, and there is a 1-to-1 mapping from set A to set B, okay, that is y1 is f of x1 and so on until yn is f of xn. So, this relationship is also valid, that means there is a relationship between y1 the members of the set B with members in set A in the form of y equal to f x. So, if that is the true if that is the case, now we know that A is a fuzzy set, B is a fuzzy set. So, the normal way they are represented is A is mu A x1 upon x1, mu A x2 upon x2, that means the members and associated fuzzy membership function. And then similarly B also, their associated membership function is mu B y1 y1, mu B y2 y2, mu B yn yn. Now, the question is that do we have to again find what is B if given A? No, because we know already y has a relationship with x in terms of y equal to f x. So, if we know what is A fuzzy set B is already known. How? Now, this y1, y2, yn, they are f x1 until f xn. We know what is x1 until xn, from x1, x2 until xn we know. So, we know y2 is y1 up to yn. So, and all that we have to do is that once we compute what is y1, y2 up to yn, because we already know the information is that between A and B there is 1-to-1 mapping. So, all that we have to do is that after computing what is y1, y2, yn, instead of mu B y1 we just have to replace mu A x1. So, that is here mu B y1 is same as mu A x1, because this is 1-to-1 mapping, okay, and so forth. Y n mu B is mu A xn. So, this is how we compute the fuzzy set B from A given the knowledge of fuzzy set A and the mapping from A to B. If we know, we already know what should be the fuzzy set B. Similarly, many to one mapping. So, in many to one mapping you see that here x1, x2, xn, x3 they are all mapped to y1 and so on. Okay. So, that means there are many members in x1, they are mapped to the same member in B. So, many members in A are mapped, like here 3 members in A are mapped to a single member in B, that is many to one mapping through the mapping y equal to f x. Simple example is y equal to x square. So, in that case minus 1 1 will map to same point in B, minus 2 plus 2 will map to same point in B. Okay. So, that is how is many to one mapping. So, given A, mu A x 1 upon x 1, mu A x 2 upon x 2 until we have the last element x n in A. So, this is our fuzzy set A. So, similarly fuzzy set B would be if we have I would not say here it can be an elements, or let us put it y m. So, m m, right. So, then the membership function associated with y 1. So, y 1 y 2 until up to y m are computed by this relationship y equal to f x, but the associated membership function is computed what is the maximum membership function associated with corresponding x here. So, that is maximum mu a x j, where x j is f inverse belongs to f inverse y I. For example, in this case if I want to find out what is mu b y 1, so that has to be in this case is maximum of mu a x 1, mu a x 2 and mu a x 3. So, these are the 3 members in A, they map to same element in B, hence the associated membership function with y 1 is the maximum membership function associated with its counterparts in A. Okay. That is in counterpart of y 1 in A, not 1, it is many, because many to one mapping. Okay. So, this is example, like here as I said f x equal to x square is a good example of many to one mapping, where minus 1 1 maps to 1, minus 2 2 maps to 4 and 3 maps to 9. So, in this case if given a fuzzy set is given like this, where minus 1 has membership function associated 0.2, minus 2 0.4, 1 0.6, 0.2, sorry, this is not 0.2, this is 2. So, 2 has 0.8 and 3 has 0.9. If this is the membership function, so B whose members are 1, 4, 9, this membership function would be like for 1 the maximum membership minus 1 1 1, minus 1 is here, 1 is here. So, the maximum is 0.6. Similarly, 4 minus 2 which is 0.4 and plus 2 is 0.8. So, maximum is 0.8, and then 9 of course is single one to one mapping. So, whatever is here will come here. So, 0.9 will come here 0.9. So, then the answer is this B equal to the fuzzy set B is 0.6 by 1, 0.8 by 4, 0.9 by 9, that means it has 3 members 1, 4, 9, and associated membership functions are associated membership index or indices are 0.6, 0.8 and 0.9. Now, we will be talking about crisp relation. Crisp relation, when we talk about relation, that means it is more than one sets, that is 2 or more than 2 sets are involved in this process. So, let us take a simple case we can have multiple sets, but we will first talking about now crisp relation before we talk about fuzzy relation. So, in a crisp relation, the Cartesian product of two universal set is determined x times y is, this is Cartesian product, is ordered pair, all ordered pair x and y, where x belongs to x, capital X, and y belongs to capital Y. So, the crisp relation mu r x y is defined as, so this crisp relation is actually is defined on the Cartesian space, product space, Cartesian product space. So, mu r x y is either 1 or 0. This is 1 if x y belongs to the Cartesian product, and 0 if x y does not belong to the Cartesian product space. So, what is meaning of 1? Now, 1 implies complete relation and 0 implies no relation. When the sets are finite, the relation is represented by a matrix R called relation matrix. I give you a simple example. Let us say x is 1 and 2 and y is A and B. Okay. So, relation means the Cartesian space is of course x times y is 1A, 1B, 2A and 2B. So, this is your Cartesian product space. Now, when I say relationship, that is, if one has no relationship with A, then the membership function the mu r x y, the relation the associated with this is 0, because that means 1 is not related to A. But if 1 is related to B, if the relationship is there, then we associate with this 1. So, that is in the relations in the relation space, the matrix R is the relation matrix, which is x is 1, 2, A and B. Okay. So, when I say the relation 1 and A, they are not related, means 0. 1 and B, they are related, means 1. 2 and A are related, 1. 2 and B are not related, 0. So, then this is our relation matrix, and because we have finite number of elements in x and y, we can always represent a relation by a matrix. But if it is a continuous set or a set having infinite points, then we have difficulty in terms of representing a relation in terms of matrix. So, this is a crisp relation. X is 1, 2, 3 and y is A, B, C. Okay. As I said earlier, we took 2 by 2, 2 element in x and 2 element y. Now, it is 3 element in x and 3 element in y, and if I represent R, then you see that if R is 1, 1, 1, 1, 1, 1, 1, 1, 1, implies all the elements in x are related with all the elements in y. So, each element in x is completely related to each element in y, that is 1A, 1B, 1C, 2A, 2B, 2C, 3A, 3B, 3C, they are all related, completely related. Whereas, in case of this particular relationship, where we have 0, 0, 1, 1, 0, 0, 0, 1, 0, it implies 2A, 1C and 3B, they are only related, others are not related. Okay. So, this is meaning of crisp relation. Crisp relation means either the relationship index is 0 or 1. Okay. There is no in between relationship. So, that is classical relationship matrix. Okay. Now, the question is that if we have multiple Cartesian product space, and we know the relationship, then can you infer the relationship? For example, here x, y, z are universal sets. Let R be relation that relates elements from x to y. So, in Cartesian product space of x and y, R is defined. Similarly, in the Cartesian product space of y and z, S is defined, the relation S is defined. Similarly, T is defined in the relationship Cartesian product relationship x and R. Okay. So, T with the relation that relates same elements in x that R contains to the same elements in z that S contains. Okay. The Cartesian space here is x times z. Okay. So, this we can do. So, if R is given, S is given, can I compute T? This is the normal question we would ask. So, if I know the relation in the Cartesian product space x y as well as Cartesian product space y and z, can I infer the relation in the Cartesian space x and z? Because x y is known, y z is known. Can I know x and z? That is the inference, knowledge inference, information inference. So, the question is yes. How do we do it? Now, given R and S, T is determined using the principle of composition, where T equal to R composition S. So, this composition can be found out either two method. One is max min composition, another is max product composition. In max min composition, the associated membership function mu t is computed as a maximum of minimum mu r x y mu s y z. I give you a simple example like this is my R and this is my R S, and then I have to find out what is T. Okay. So, let us say R is x. So, x1, x2 and y is y1, y2. The relationship is 0, 1, 1, 0. Okay, let us say, and similarly S is from y and z. So, y1, y2, z1 and z2. Okay, and let us say again the relationship is 0, 1, 1, 0. That is the case. Now, I have to find out what is the relation between x and so z1, z2. So, how do I find out in this max min composition? In max min composition, you see that what I find out, I want to find out now what is x1 and z1. Find out x1 and z1. Okay, x1 and z1. So, how do I find x1 and z1? So, 0 1 you bring here 0 1. Okay. It is like matrix multiplication we do. So, this row you put parallel to this column, okay, over y1 and y2 here, because and then 0 0 the minimum, this is 0 mu r x y, okay, mu r x y is 0 and mu s y z this is 0. Okay. So, minimum of that is 0. Okay. The first minimum is 0, and then second over all y, similarly x1 y2 x1 y2 and y2 z1. So, that is 1. So, x1 y2 is 1, y2 z1 is 1. So, you find out that it is very simple. All the basic principle is that the 0 1 you put parallel with 0 1, find the minimum in each case. So, what I can do is that for 0 1 I have another 0 1 here, parallel comes from here, and find the minimum from 0 0 is 0 and 1 1 is 1, and find the maximum from this. So, you put it here x 1 z 1, okay. And similarly I have x 1 z 1, similarly x 1 z 2, x 1 z 2. How do I find? Again 0 1 you put it here, 0 1 0 1. So, obviously here minimum is 0, minimum is 0, maximum is 0. Similarly 1 0 x 2 z 1, x 2 z 1. So, 1 0 1 0. So, you can easily see this is 0. Similarly 1 0 1 0, this is 1. So, max product composition will also lead to the same thing, because this is Cripps relation. In Cripps relationship, whether I follow max product or max mean, both will yield the same result. Like what is product means, you just multiply 0 1 0 1, multiply. So, 0 0 is 0, 1 1 is 1, and maximum of that is 1 here. Similarly 0 1 1 0 here. So, here 0, here 0, if you multiply and then take the maximum, that is 0. Similarly 1 0 0 1 you get here 0, and 1 0 1 1, if you multiply, that will come, one element is 1, another element 0, and maximum is 1. So, this is called a composition, okay, the principle of composition. So, given two relation R and S, I can compute what is T using this two rules. How to find out? In this case, this is max mean composition, this is max product, this dot means product. I multiply mu r x y into mu s y z. The example again I showed you, but this is a little more elaborate. You see that R is a Cartesian product where x is 3 dimensional, y is 4 dimensional, s is y and z where y is 4 dimensional and z is 2 dimensional. Obviously, T has to be a relation from x to z, which is 3 dimensional in x and 2 dimensional in z, using the compositional rule. So, you can easily find out that see, if it is 1 0 1 0, you put here 1 0 1 0. So, obviously in every case minimum is 0. So, you get 0 here, okay, the maximum of that. Similarly 1 0 1 0, you put here 1 0 1 0. So, obviously this will be 1 here, and 0 0 0 1 0 0 0 1. So, obviously in this case again the although 1 is there, minimum is 0. So, the total maximum is 0. So, what we are trying to do is that you take this row and take this column, you put them like here, this is this row, this column is 0 0 0 0, and this row is 1 0 1 0. To find out the relationship between x 1 and z 1, what I do, I take this row which is 1 0 1 0 and this column 0 0 0, and find for each one what is minimum. So, minimum in this is 0, in this is 0, in this is 0, and this is 0, and overall what is maximum, that is 0. So, this 0 entry comes. Now, I want to find out how this one entry came. This one entry, to find out this one entry x 1 and z 2. So, x 1 means you take this row which is 1 0 1 0, and z 2. So, z 2 means the corresponding column, that is 1 0 1 0. So, now you individually find out what is the minimum of this. This is 1, this is 0, this is 1, this is 0, and what is the maximum of all these elements, that is 1. So, that is your 1. This is called max min composition, and you can do also max product composition, you will get the same answer. So, user you should note, you should verify that in case of crisp relation, max min or max product will yield same result. Now, we will be talking about fuzzy relation. Fuzzy relation, if x and y are two universal sets, x and y are two universal sets, the fuzzy sets. The fuzzy relation R x y is given as this is all ordered pair mu r x y upon x y for all x y belonging to the Cartesian space x and y. So, you associated mu r x y with each ordered pair. So, what is the difference between fuzzy and crisp relation? In fuzzy, this is missing here, where mu r x y is a number is in 0 and 1. So, mu r x y is a number between 0 and 1. This is the difference between crisp relation and fuzzy relation. In crisp relation, it was either 0 or 1, it is either completely connected or not connected, but in case of fuzzy, it is connection is a degree, that is it is from 0 to 1. So, the example is, let x equal to 1, 2, 3, x has 3 members, y has 2 members 1 and 2. If the membership function associated with each ordered pair is given by this e to the power minus x minus y whole square, you can easily see this kind of membership function is used to know how close is the members of y from members of x, because you see that if I relate from 1 to 1 using this, then you can see 1 minus 1 is 0, that is 1 and 1 very close to each other, whereas 2 and 1 is a little far, and 3 1 1 is further far, that means they are more apart. So, this is a kind of relationship we are looking at between these two sets, fuzzy sets x and y. So, now let us derive fuzzy relation if this is the membership function. So, fuzzy relation is, of course, all the ordered pairs we have to find out 1 1, 1 2, 2 1, 2 2, 3 1 and 3 2. These are all the sets of ordered pairs, and associated membership function you just compute e to the power minus x minus y whole square. So, here 1 1, 1 minus 1 whole square, 1 2, 1 minus 2 whole square, 2 1, 2 minus 1 whole square, 2 2, 2 minus 2 whole square, 3 1, 3 minus 1 whole square, 3 2, 3 minus 2 whole square, and if you compute them you find 1, 0.43, 0.43, 1, 0.16, 0.43, right. So, this is your membership function. This is one way to find relation, but normally it is easier to express the relation in terms of matrix instead of this continuum fashion, where each ordered pair is associated with membership function. It is easier to appreciate the relation by simply representing them in terms of matrix. And so, how we do that? So, this is my x 1 2 3, y is 1 2. So, 1 1 the membership function associated was 1, 1 2 membership is 0.43, 2 1 0.43, 2 2 1, 3 1 0.16 and 3 2 is 0.43, that you can easily verify here 1 3.43, 0.16 and 1. Okay. So, since the membership function describes the closeness between set x and y, so it is obvious that higher value implies stronger relation. So, what is a stronger relation is between 1 and 1, they are very close to each other, and 2 and 2, they are very close to each other. So, closeness between 2 and 2, closeness between 1 and 1 is actually 1 and 1, they are very close to each other, closest. Similarly, 2 and 2, if I simply say numerical closeness, then 2 and 2 they are the closest, and 1 and 1 they are the closest, and that is how these are the closest. Higher value implies stronger relation. So, their relations is the strong. So, this is a formal definition of fuzzy relation. A fuzzy relation is a fuzzy set defined in the Cartesian product of crisp sets x 1, x 2 and x n up to x n, and a fuzzy relation R is defined as mu r upon x 1 to x n, okay, where x 1 to x n belongs to the Cartesian product space of x 1 until x n, okay. Whereas this mu r, the fuzzy membership associated is a number between 0 and 1. Now, we will be talking about projection of fuzzy relation. A fuzzy relation R is usually defined in the Cartesian space x and y. Okay. Often a projection of this relation on any of these sets x or y may become useful for further information processing. So, the projection of R x y on x denoted by R 1 is given by mu R 1 x is maximum y belongs to y mu r x y. So, the meaning is that if I have R which is, let us say, x 1 and x 2, and this is y 1 and y 2, okay, and this is 0.1, 0.4 and this is 0.5, 0.6. If I, these are the membership function associated with x 1 y 1, x 2 y, x 1 y 2 is 0.4, x 2 y 1 is 0.5, x 2 y 2 is 0.6. So, projection means, so for x projection I find out what is the maximum over all y. So, in this case maximum is 0.4, and for x 2 the maximum projection is if I took it here 0.6. Similarly, if I make projection of R x y on y, so over x what is the maximum? So, this is 0.5 and this is 0.6. Okay. This is called x projection and y projection of a relational matrix R. So, this is again for your benefit, again we repeat another example. So, we have x has 3 components 1, 2, 3, y has 2 components 1 and 2. This is the previous example that we had 1, 0.43, 0.431, 0.16, 0.43. So, x projection would be 1, 0.43 maximum 1, 0.431 maximum 1, 0.16, 0.43 maximum 0.43. This is x projection. Similarly, y projection I look at here, this is maximum is 1 and here maximum is 1. Okay. So, this is my y projection of relation R and this is my x projection. So, above figure illustrates x and y projection of fuzzy relation. For x projection, the maximum value in each row is retained. Here the what is the maximum value in each row, sorry, x projection maximum value in each row is retained, while the maximum value in each column is retained for y projection. Okay. So, this is our formal definition of a fuzzy relation. Projection of a fuzzy relation R onto any of its set in the Cartesian product space, that is in the Cartesian product space. This is our Cartesian product space, and for we can we can map this one to any of these I or j or k, whatever it is, for any of this value, then is defined as a fuzzy relation R p, where R p is defined as maximum over x I until x k, where this is our x I, x j, x k, and this is mu R p. So, we talked about fuzzy, first we talked about fuzzy relation, projection of fuzzy relation. Once you have projection of fuzzy relation, we can extend the projection to again infer what should be the relation. This kind of technique may be useful in coding the information, where we have a huge number of information and we want to transfer them. So, such kind of projection and from projection to extension would be beneficial for coding operation. So, now let us understand what is extension of fuzzy relation. Cylindrical extension from a x projection means filling all the columns of the relational matrix by the x projection. Similarly, cylindrical extension from y projection means filling all the rows of relational matrix by the y projection. So, now this is my x projection in the previous example 1 1.43. So, what I do is that when I create a relational matrix between x and y, then all that I do is that I fill all the rows with 1, here all the rows with this 1 and all the rows here 0.43. Whereas, in y projection, if I had and I extend to the relation, then from y I fill all the columns here. So, this is 1 filled with all 1 and 1 filled with all 1. So, that is how the we have the actual relational matrix projection, and again from projection, obviously this is not a very good kind of extension, but this is known as cylindrical extension. There may be other methods how to extend from projection to the actual relational matrix, that is a different question altogether. So, now we learnt about what is relation, we learnt about what is projection, and from projection to extension. Now, we will be talking about given two relation, just like we learnt in crisp relation, that given two relation, the third relation can be inferred through composition rule, max min as well as max product. They are equally valid for fuzzy relation as well. So, let us define R 1 over Cartesian space x and y, R 2 over Cartesian space product space y and z, R 3 over Cartesian product space x and z. So, if R 1 and R 2 are given, then R 3 is inferred using either max min composition, as we have already discussed, or max product composition. The same principle, I will not explain this again, because the only thing is that earlier this mu r used to be in crisp relation, they used to be either 0 or 1, whereas in fuzzy it can be any number between 0 and 1. So, we will now explain max min composition operation using an example that makes things much more clear. So, this is my matrix, relational matrix R 1 relating x and y, and R 2 relating y and z. Now, I have to find out the relational matrix from x to z, using fuzzy rule of composition. So, we normally write R 3 is R 1 composition R 2, right, and using max min composition, how do we compute R 3? Is very simple. So, I want to now build a relationship between x, this is the membership associated with x 1 and z 1. So, let me put it very precise, x 1, x 2, x 3, z 1 and z 2. So, if you look at what we will be doing here, this is my x 1 row. So, and my z 1, this is my z 1 column. So, what I do, x1 row and z1 column. I put them parallel and find out what is minimum. Here minimum is 0.1, here minimum is 0.2, and after that I find out what is maximum, that is 0.2. So, this is what maximum, minimum 0.1, 0.9, minimum 0.2, 0.7 is 0.2. So, this is how we found out. So, the easiest way, just like if I want to find out this one, this x1, x2 and z1. So, x2 means this row which is 0.4 and 0.5, and x2 and z1 is again 0.9 and 0.7. So, I find out what is minimum here is 0.4, what is minimum here is 0.5, okay, and what is maximum here is 0.5. So, you get this 0.5, right. So, similarly, we can compute all the elements in R3 using max min composition operation. As usual, in max min composition, it can it follows certain properties, associative and distributive over union, that is P fuzzy composition, fuzzy composition Q union R is P composition Q union P composition R. Similarly, weakly distributed over union, that is P composition Q intersection R is a subset of P composition Q union P composition R. Monotonic Q is a subset of R, implies P composition Q is a subset of P composition R. Okay. Fuzzy max product composition operation. So, earlier we talked about max min, now we will talk about max product, max product. As you know that in case of crisp set, both max product and max min they yield the same result, but in this case it will not, and that we will see now. Max product means how do we do? Now, again the same example we have taken R1, R2 and R3. Now, I want to find out from R1 and R2 what is R3 using max product composition. So, to do that, what I do is again I do the same thing. Let us say this is x1, x2, x3, z1, z2, z1, z2, and this is x1, x2, x3. So, for x1 I take this row which is 0.1, 0.2, and for finding the relation the fuzzy membership associated with x1 and z1, I take the column from z1 which is 0.9, 0.7, and I multiply them here. 0.1, 0.9 is 0.09, 0.2, 0.7 is 0.14, and find out what is the maximum. So, this is the maximum. So, 0.14, right. Similarly, I want to find out, I take another example, let us I to find out the relationship between x2 and z2. So, for x2 the column is 0.4, 0.5 row is 0.4, 0.5, and z2 the column is 0.8, 0.6. Okay. So, corresponding to this, if I multiply I get 0.4, 0.8 is 0.32, 0.5, 0.6 is 0.3. So, maximum is 0.32. So, this is 0.43, 0.32. So, this is where so you see that this is 0.1, the answers here the R3, and if I go back, if I look at the R3 here is different, So, now we will take consider another example of fuzzy relation. little more application oriented. So, let us think of two different sets of objects. One set of objects are images collected from various objects like car, boat, house, bike, tree, mountain. We have such images, right. And now the geometry of these images can be compared to various known geometries like square, octagon, triangle, circle, ellipse, like that. Okay. So, now the question we may ask is that if I have an image of any of these objects like car or boat or house or bike or tree or mountain, how close these images are to an image of a car. Okay. This is a question I pose. My question is that how close an image of car is to those of either a car or a boat or a house or a bike or tree or mountain, and I create a fuzzy set and I call that fuzzy set to be a car. So, my fuzzy set A is a car fuzzy set. So, obviously, when I compare image of we look at a car image, obviously the membership is 1 because car, and boat may not look like a car, but is the fuzzy index is 0.4. Obviously, a house will not very less likely to look like a car. So, fuzzy index is 0.1. A bike may look like a car with fuzzy index 0.6, a little more, whereas a tree is similar like house, a very little resemblance with a car with a fuzzy index 0.1, whereas a mountain may not have any similarity with the car. So, 0 fuzzy index. So, when I want to look at all these objects and infer whether they are car, the associated membership functions are 1, 0.4, 0.1, 0.6, 0.1 and 0. Similarly, I look at the various geometry and I want to infer whether this geometry is a square. So, obviously, if I am looking at a square, actual square, the fuzzy membership is 1. If it is an octagon, then it is 0.5, triangle 0.4, circle 0, ellipse 0.1. Now, the third is that these geometric objects, whether they have corners, the square will have 4 corners, octagon has 8 corners, triangle has 3 corners, circle has no corner, and ellipse although it does not have exactly corner, but it may appear like to have some corners. So, you see that when I look at the fuzzy set of a corner, then square will have fuzzy membership 0.6, octagon has maximum number of corners, so 0.9, triangle has 3, so 0.4, circle has no corners 0, and ellipse 0.2. So, this is how we fuzzify the set car, square and corner. Now, we would like to establish the relationship between car and square, square and corner, and then infer the relationship between car and corner using fuzzy inference composition rule. So, find a relation R between car and square, find a relation S between square and corner. Using max-min composition rule, find a relation T between car and corner. So, this is the question. So, if I just the relationship matrix between fuzzy set A and B. So, what was A? A was the set which is car, and we defined this fuzzy set to be this way. Car was 1 by car, 0.4 boat, 0.1, house, 0.6, bike, 0.1, tree, 0, mountain. So, this is my car subset, fuzzy set, and B, which is my square subset, is 1 upon square octagon has 0.5 and a triangle 0.4 and circle has probably membership 0 because circle will never look like a square. Ellipse is 0.1. So, how do I find the relationship R? So, you can easily see here this is square, S stands for square, octagon, triangle, circle and ellipse, and this is my B set and this is my A set. In A set the elements are car, boat, house, bike, tree and mountain. Okay. So, how do I find these members here? All that I have to do is that each element, because I have to create an ordered pair and take the minimum membership function. Okay. So, car will be made ordered pair with a square, octagon, triangle, circle and ellipse. Car, circle, octagon, triangle, circle and ellipse. And with car, when I say square, the minimum membership function is 1. Car with octagon, minimum membership is 1, between 1 and 0.5 is 0.5. Similarly, car and triangle, the minimum membership is between 1 and 0.4. So, 0.4. Similarly, car and circle, between the minimum between 1 and 0 is 0. Car and ellipse is between 1 and 0.1, minimum is 0.1. Similarly, I would find out the relationship between B and all other elements in the boat in set A with all the elements in B. So, boat has a membership function 0.4. So, when I compare a square, obviously the minimum is 0.4. So, 0.4 and then with octagon 0.5. So, because this is 0.4, 0.5 I have 0.4, 0.4, 0.4, 0.4, 0.4, 0 is 0, 0.4, 0.1 is 0.1. So, like that I can fill all these entries. So, what is the method? Method is that in each ordered pair I find out what is the minimum of the membership function. So, any, for example, if I make an ordered pair between this and this, okay. So, minimum is 0.4 and 0.1 is 1, 0.1, 0.4, 0.1, 0.4, 0.1 is 0.1. So, you can easily see this is triangle and this is tree. So, this is tree, triangle and this is tree, and their relationship is 0.1, the membership. Okay. So, this is how we find out the membership function between A and B. Similarly, this is the relationship between B and C. B and C, this is the relationship. Okay. So, this is set B and this is my set C. Okay. Set C. So, set B is square and set C is the corner. So, once I found what is R and S, the next is to find out the relation T. So, relation T between car and corner can be found out using inference mechanism, which is composition rule. We have used this is max mean composition. So, this has been found out using max min composition, and as I explained earlier how to find out max min composition. But what I would like to show you here, the same matrix, that relation matrix that I have got, I can also get directly from, this is my A and this is my C. So, A stands for car. So, my car was 1 upon car and 0.4 by boat, then 0.1 by house, 0.6 by bike, 0.1 by tree, 0 mountain. This is my car, and C is corner, which is the corner, the square is 0.6, octagon has maximum number of corners, so 9.9. Then triangle has 3 corners, so 0.4. Circle has no corner, and finally ellipse may look like have some corners, so 0.2. So, although this matrix we found by max min composition principle, the same thing also you can find out simply looking at these two sets, car and corner. So, you can easily see that when I relate car with this thing, so you should say, because car has membership function 1. So, all these membership functions which are always will be minimum with respect to 1. So, they will be there 0.6, 0.9, 0.4, 0 and 0.2. Now, next if I go to boat, 0.4. So, 0.4 is minimum here, 0.4 is minimum here, 0.4 is minimum here. So, first 3 will be 0.4, 0.4, 0.4, and then 0 minimum here, 0.2 minimum here. So, exactly whatever I got from inference mechanism, the same mechanism, same inference, same thing I will get using directly looking at car and corner. Okay. So, finally, the summary, what we discussed today are, we extended the function mapping concept to fuzzy sets, we the crisp relation and fuzzy relation, the difference was discussed today, where we showed that crisp relation, the index is either 0 or the membership grade is either 0 or 1, that is either complete relation or no relation, whereas in fuzzy the relation has a grade from 0 to 1. Fuzzy composition rule, max min composition, max product composition, unlike in crisp relation where both max min and max product gives you the same answer, whereas in fuzzy composition max min and max product will give two different answers. And fuzzy projection and cylindrical extension we discussed, and also we showed illustrated all these principles through various examples. Thank you very much.